Hello, this is Steve, E6WZ. I'm going to call this a companion video to two papers that I recently uploaded. One describes my two-element parasitic transmit array for 160 meters, which is at my remote station. And more recently, an article that explains a new feed system to my two-element 80 and 40 meter inductor loaded Yagi that allows for 180-degree direction switching. In both of those papers, I talk quite a bit about the relationship with mutual coupling on a parasitic element in an array, and how by observing the impedance curves of those arrays you can quite easily, with some field testing using an antenna analyzer, tune the array with confidence for maximum gain in front to back, though I'm also going to talk about a few other things. The hope here is by using, and I'm going to run Fornec 2 during this video it might give some guys here that have not maybe used Fornec a little bit of a snapshot into it, but this is not a tutorial on how to work Fornec 2. But it might help see where the data came from and comes from that I've described in the two papers that I just talked about. Four things I'm going to focus on. One is I'm going to show the effect simply of mutual coupling when a parasitic element is present in a model. I'm going to just show the relationship between maximum coupling point and the gain in front to back. And in fact, this is very important in terms of how it relates to being able to, with confidence, tune a two-element array of any type. Thirdly, I'm going to show the effect of relative tuning on the 2-to-1 SWR bandwidth of any two-element array. And then I'll discuss how, as I said, any two-element array can be tuned on a tower using just an antenna analyzer and being armed with a model. So to start with, we'll talk about mutual coupling. And a single dipole element will just have a gradually increasing real resistance with frequency, and it'll look like this. This is a chart from Fornec 2, and I'm going to actually run Fornec 2 in a minute and create this display. But just as a snapshot here, this is what we call the impedance chart from the program, and it's plotting frequency on the bottom. In this case, I've chosen from 3.7 megahertz up to 3.9 megahertz is the frequency span on this plot. The two curves in red is reactance, and the resonance point is found when we cross 0 ohms of reactance. This is positive reactance and negative reactance, and this is showing the resonance point of the, in this case, dipole element. Important to notice is in blue is the actual real resistance of that element, and it ranges from 20 ohms up to about, say, 28 ohms. So how do I create this in Fornec 2? This is a diagram right here of the input screen. Now, I am not going to go into details about my model, and I could have chosen to just put a very simplistic model in here of just the dipole element, but since later in this video I'm going to talk about details of my two-element short loaded Yagi, I thought I may as well show the full model. There are four elements in this model. The longest elements, which are shown here and here, these are the 80-meter elements. They're about 60 feet long in the model, and they're spaced exactly 28 feet apart. The 40-meter elements are coincidentally 40 feet long, and they're spaced only 15 feet apart, and they're interlaced on the 28-foot boom. In order to resonate the elements, there are inductors included on each of these, all of these elements. And at the top banner here in Fornec 2, you can toggle RC loading, and then it will highlight the individual inductors. So in fact, I could toggle this inductor here, and you'll see that it's a series RLC load. It's 26.5 microhenries, and I include a zero point 0.5 1/2 ohm series resistance in each of my inductors to account for series losses of the inductor. Even though they're high Q coils, they do have loss, and in order to at least try to accurately represent the relative gain, I've included these series losses. There are 4 of these inductors for the 80 meter Yagi, and on the 40 meter Yagi, there are 12 microhenries, and there's 4 of those. Again, I'm not going to talk about the details of where they're placed or anything like that. Yeah, the elements are, there is no taper. There's no diameter tapering done on this. This is a very simplistic model. The elements are 1-inch diameter elements made of aluminum. Now, with respect to that, I do not endeavor to create extremely accurate, properly tapered diameter elements for my antennas simply because my main use of modeling is to provide a relative notion of tuning of individual elements and relationships, and I'll talk more about that. So I don't rely on exact impedances to calculate matching networks or anything like that. I could go to 3D view and show the antenna, and these elements are located at 90 feet to represent the antenna being modeled at 90 feet. For the moment, actually, none of that's important, but that's the basics of the model. So to move forward, I'll place a source. So I toggle the source at the banner, and in this case, I'm going to plunk the source in the middle of the 80 meter element here. In order to model this as a dipole element, I need to eliminate the presence of this other element, and I do that by toggling the loads. I'll highlight the load on this element. You can see that I actually do have an inductor in here, which is meant to represent its moving it to become a reflector, but that's not important. To make this element disappear, for the resistance, I'll include, say, 1,000,000 ohms, okay, at the feed point. So basically, this element now is removed from the circuit because it's completely non-resonant resonant on 80 meters. So I've got my source in the middle, and this is my element. So in order to do a sweep, I'll go to Calculate, and I'll do Calculate Neck Output, and a screen like this pops up, and I'll do a frequency sweep, and I'll do a range from 3.7 to 3.9, and I can choose my step. In this case, I'll stay at 1 kilohertz, which is very narrow and takes a fair bit of computing time, but it provides lots of detail to view. And then I'll go Generate, and it'll proceed to generate that plot. So as you can see now, the plot has finished computing. And what I'll do is I'll go to the impedance toggle, which you can see up in the upper right corner. And this is the curve, which looks perhaps similar to the one that I just showed you. And you can see that in blue is the resistance, and here is the crossing point of zero reactance, which would represent resonance in and around about 3873 or so. And at that point, the impedance, or not the impedance, the resistance is about 24 ohms. So now let's go back to my model. So this is the dipole element. Now let's go back to my model, and I'll edit my input file. And what I'm going to do is I'm now going to go back to my loads. I'm going to select this load on this element, and instead of 1,000,000 ohms, I'm going to just put 0.05. This is a very small resistance, which again is meant to represent a small amount of losses in any kind of loading device at the center element. And then I will calculate, do the same sweep again, calculate my calculate a frequency sweep over the same frequency range with the same step, and I'll generate that. And there the computation has completed. And now if we look at the impedance plot again, we'll notice that instead of a steadily increasing flat resistance curve, we now have a very pronounced dip. And this dip, you can see if I highlight it, is gone down to about 5 ohms, as opposed to, if you recall, it was about 24 ohms. at resonance. Now also the resonance point has perhaps moved slightly, and that's because of some coupling and loading down of the driver. The important thing to notice here is that this dip basically is entirely a function of the parasitic tuning. So I'm going to go back to my PowerPoint, and so this is easier to show, but I just wanted to show on Fornec 2 how I actually make these calculations. And I've just brought that same curve that I just made and put it right under the other one. So there's the two examples. This is a single dipole element with no parasitic, and as soon as I introduce a parasitic, the 5 ohm dip is clearly seen. And again, this is entirely because um, of current being induced or coupled into this parasitic element at that frequency. And basically this causes the resistance to drop in the driver because of the RF power now is being shared between both of the elements. And for better or for worse, I like to view this almost as though there are now two resistors in parallel. So we've dropped the impedance, or again, the resistance of the driver, because current is now being induced into that element. And in fact, in Fornec 2, if one were to look at, you can actually show currents on the element, and you'll see that at this frequency, the current is quite high in that parasitic element as it's being induced. And this current that's being induced in the parasitic element is what causes the pattern to be formed in a two-element array. In fact, to show that, I'll go back to this same model that I just created in Fornec 2, and you'll notice if I press the gain button up in the upper right, I can now look at the gain and front to back profile of this two-element Yagi. You'll notice that on the bottom curve in red is the front to back, and you can see that it was about 19 dB of front to back at this point. And at the top, you can see the gain profile in blue. What you can notice here are a couple of things, not the least of which is on the front to back profile, it crosses 0 and actually becomes a negative front to back. Well, in fact, what that is the array is becoming a director at this point. So on this graph, I've put all of the curves together. Fornec 2 doesn't offer a plot that puts them all on one page, so in the PowerPoint here I've done that. On the bottom is the impedance curve, of course, showing that dip in the real resistance, the point of maximum coupling, shown here at around 3.8 megahertz thereabouts. So that's the point of maximum coupling. And the most important thing to notice here on this image is the relationship between this dip in the impedance and the maximum front to back on the red curve shown here. In fact, the line is running through that, and the maximum gain. And in all cases, the maximum gain and the front to back are slightly above in frequency, slightly above and higher in frequency than that maximum, the point of maximum coupling. It turns out, in fact, that if you were to go below the point of maximum coupling, lower in frequency, then you would reach the point of maximum gain and maximum front to back in the case of this being a director array. But in the case of a reflector array, the point of maximum front to back and maximum gain are found at so many kilohertz above this dip. The other thing pointed out here is the fact that as I pointed out earlier, the maximum front to back point is not coincident with the maximum gain point. And in fact, it rarely, if ever, in a two-element array are the maximum gain and maximum front to back points coincident. They're more often than not offset by a certain amount. And as I mentioned earlier, the point of inflection at which the array reverses direction and becomes a director. So perhaps in summary, the point that is I'd like to portray here or make sure is understood is that by knowing and field measuring the impedance of any two-element array in the field using your analyzer, as I'm going to talk about later, you can identify this point of maximum coupling. And using the model as your guide, you can then uh, confidently know that if you were to tune the Yagi so many kilohertz above that frequency, you will be at the point of either maximum gain or maximum front to back or wherever you wish to tune the array. And in fact, that's what I'll be talking about next, is the effect of the location of tuning and SWR. So um, before I talk about the details of that, one interesting point here to notice is that although peak gain is often quoted um, commercially, and anyone will, even in homebrew Yagis, will tend to quote the peak gain. The truth is, achieving peak gain is actually difficult to actually achieve in practice. Um, and hopefully you can see why in this graph, because um, with this particular Yagi, especially because it's a shortened Yagi, the bandwidth performance is very narrow. That is to say that you can see that at the peak gain point, it's 9.4 dB of gain at the peak, but only so many kilohertz down, I'm already 1 dB down in gain. And as I move even further down frequency, I've even lost perhaps upwards of 2 dB of gain. So the gain performance or the gain profile is never ever flat on a Yagi. And the same is true, and for that matter, even more dramatic for front to back. The front to back peak and is often, especially in a shortened Yagi, quite narrow. And so what I want to talk about now are the limits of 2-to-1 SWR bandwidth, especially as it relates to a loaded Yagi. And by the way, this performance, that is to say, the gain bandwidth performance and the front to back bandwidth performance is predominantly a function of element length. Of course, in the case of a shortened element, it becomes very narrow, and also a function of boom length and spacing. So with the model that we've built, we can tune the Yagi driver at any frequency we choose, and the gain and front to back profile will always remain only a function of the parasitic directory. In other words, that will never change, the profile of the gain and the front to back. And the way we do that within the model, and I'm going to do that is right now, is use ForNec2 and use a kind of a handy function they have called the L-matching network function, and experiment with matching this very Yagi model at different frequencies to study the SWR bandwidth. So I've opened up the ForNec2 window here. In fact, this is the same window we just saw, showing the gain and front to back profile of the two-element Yagi on 80 meters. Perhaps to start the experiment here, how about if we say, okay, let's take this Yagi that we have and let's tune it for the maximum gain. Let's tune this the driver so that the one-to-one SWR will be right at the peak gain point. So if I put my cursor here, then I could say, for example, go to the impedance curve, and I can see that, well, my reactance is negative 22, and the real resistance is 10 ohms. And so I'm going to show you now a pretty handy functionality within ForNec2. And if we go to the main window here to the left, you may see I can go to something called Calculate. And here's a function called LPIT matching. And this brings up a window that looks like this. And so you can see here at the frequency of 3812, close to where we want to tune, it shows the load of the antenna as 10 ohms real and about minus 21 J, or the reactance. And so what you can do is you can select the network you want to use. I usually use just a regular low-pass L network, and it's showing that in this instance it would be 1.73 series inductor and about 15 picofarads as a parallel capacitor. Anyway, you select that and you say, let's just go ahead and use that network. And then the dialog box will come up that asks you, okay, now how about we do a frequency sweep using that matching network. So we go ahead and generate this and see what it shows us. Okay, so the curve has come up now and finished doing the calculations, and the first curve that came up actually is the SWR profile shown in blue here. So now, using that L network, it has matched the feed point at the frequency we chose, which we wanted to be the peak gain point. It has matched that reactance and real resistance to a 50 ohm load. And this is what the SWR profile will look like. Well, in fact, you can see the 2 to 1 SWR point is here. You can see 2 to 1 on the left is at 3808, and the other 2 to 1 point is about 3818. So this is 10 kilohertz, 10 kilohertz of bandwidth. So that would be what you'd call, I would submit, virtually unusably narrow. But if I put my cursor here, so 1 to 1 is this point, and if I go to my gain response, there we are. So I've now tuned the the Yagi to have a 1 to 1 SWR right on the peak gain point, but that's entirely impractical because this is virtually an unusably narrow bandwidth. Now, how about if we then say, well, okay, how about we tune the Yagi out here at say, oh, I don't know, like say 3830 or so out here and see what happens, because we can do that. And I'll show you how we do that. So we'll go to edit, and we edit the input file. And what we do is this is important, this is a bit of a trick, you have to do it this way, and we change the frequency to 3830 of our model. So you can see I've input 3830 here. And then what we'll do then is we'll calculate the neck output. We have to do a frequency sweep and do a run. So what I tend to do is just do a far field pattern sweep, because that proves to be sufficient to adequately populate the matching network module. So now we go to the LPT matching network, and you'll see now, I need to close this, I'm sorry, and then we pull up the LPT matching network, and now you'll see that it's been populated to be the design frequency at 3.83. And now you'll notice that the reactance or the real resistance is 28 ohms and minus 4 for the reactance. So significantly different at this frequency. So again, we'll select our L network, and we'll use that network and then generate another frequency sweep and see what the SWR profile looks like with the Yagi tuned at 3830. All right, so the run is finished, and okay, so here is our SWR profile. So the 1 to 1 point is as we expected at 3830 using that matching network. And now, gosh, I can look at my 2 to 1 limits back here at 3818, and gosh, it goes all the way up to 3883, 3885, thereabouts. So this bandwidth now, 2 to 1 SWR bandwidth, is a full 65 kilohertz or so. So this looks great. I mean, a very compelling SWR bandwidth performance. So if I then, though, look at, say, the center 1 to 1 response and go back to my gain profile, you'll see that, well, gosh, I'm down here at 8.64 dB. I'm quite a ways off from the peak. That's almost a dB off. But on the other hand, okay, if I go down to my 1 to 1 point, I'm sorry, my 2 to 1 SWR low end, and still keep my amplifier happy. If I look at my gain here, well, I'm almost at the peak front to back, but I'm quite a ways off of the peak gain figure. But perhaps most importantly is a lot of this, what might be considered usable bandwidth from an SWR standpoint. If I'm all the way down here and using the Yagi down here, down around 3888, if I look at the gain, I'm down at 7 dB of gain versus 9.3. So I've lost fully 2 dB of gain down here. So the point here is, even though this is very compelling from the standpoint of a broad SWR, in actual practical speaking, you're greatly losing gain down here. And so what I'll do now is go back to my PowerPoint, because at least now you've seen the methodology used to generate these curves. Okay, so in this display, I've essentially included on the top, the gain curve, which we just saw in the actual Fornec 2 models that we built, and then included 4 of these very same SWR bandwidth curves that we just created. In fact, the first one is the one that we did initially, and that is to say it's tuned for a 1-to-1 SWR at 3812, which was and is the maximum gain point. And as we discussed, there we have it. We only have a 10 kilohertz bandwidth, which is, very narrow, but again, I mean, gosh, it's narrow though it is, it's completely contained within the maximum gain point of the Yagi. But 10 kilohertz would be tough to work with. And I must say, I must add, the other issue here is, if you ever did even want to tune a Yagi like this, you're also dealing with a significantly lower feed point impedance than you would if you moved further up frequency. And that can be a challenge, and can lead to diminished gain because of series losses when the resistance is low at the feed point. So that's a kind of a downside for wanting to do something like that. The second SWR curve is tuned for 1-to-1 SWR at 3817. That happens to be the maximum front to back point as the Yagi's tuned. And here you'll see the 2-to-1 SWR bandwidth is about 16 kilohertz. So, it's definitely a little bit more broad, definitely at the low end, contained within the peak gain point. Obviously is right on the peak front to back point, and is maybe worthy of considering using, but boy, that would be a challenge to spread a Yagi like that across the band. So the third chart shows the Yagi tune for 1-to-1 SWR at 3812. Okay, so only slightly above the front to back frequency, and it shows a bandwidth of 30 kilohertz. And in fact, as I'll discuss later, this is kind of the target that I used for my Yagi, because I feel it's a good compromise between bandwidth and maximizing my gain. For example, on the low end of the 2-to-1 SWR curve, I'm still pretty close to maximum gain, and on the low end, I'm down about 1 dB gain from the peak. And the last curve is the one which I just finished running with Fornec 2 with the Yagi tuned at 3830. And there you can see, again, what appears to be perhaps a compelling bandwidth of 65 kilohertz. But in fact, much of this, what might be considered usable bandwidth from an SWR standpoint, is significantly down from maximum gain. So there really is no free lunch, especially when it comes to a loaded Yagi like this, because the bandwidth response is very limited, and the peak gain and front to back are achieved really only over a very narrow operating window. And that's why with my Yagi, and in the paper I wrote and described, I've implemented band switching. Um, and band switching with inductors at each element. And that's the point. It's not just tuning and band switching and adjusting the driver for a match. You must tune the reflector to follow and move the Yagi across the band, and that's critical. Uh, One other thing that's obvious here, but I'll just point out, is to notice that actually the maximum gain is in a reflector model is always at the low end of the SWR window. In other words, it's always at the close to the 2-to-1 uh, match on the low end where you actually achieve the best gain for a Yagi. And one last thing I'll point out here is this issue is especially accentuated and amplified with a short loaded Yagi, but it is still reality for even a full-size Yagi, though less so, and can be manageable. But all Yagis will show diminishing gain away from the peak gain point. And there are other designs, OWAs and other tuning methods that can enhance the bandwidth profile and the bandwidth performance. But what really matters is the gain bandwidth. So even though the SWR might look good, that doesn't necessarily mean that it's a maximum performing antenna. In other words, there's the saying, which is common out there, and it's so true. That is to say, SWR bandwidth alone is not a measure of the performance of a Yagi. So I'm going to move on now and talk about tuning two-element parasitic array. And this is um, valid for a Yagi or a vertical array using your antenna analyzer. And as I said at the outset, this video is perhaps a companion video as well for my 160 meter two-element transmit array as well, because I talk about using this same process to tune the parasitics for that as well. So the key here and the trick is to sweep the driven element of any parasitic array um, and look for the strong dip in the real R, as we've seen before on the impedance plot, and know that this is only a function of parasitic tuning. So this is an actual image from the analyzer that I actually ran this summer on my two-element 80-meter Yagi. It's using the AIM 4170 analyzer, and I'm sweeping the driver, as I say, of the two-element Yagi with the reflector tuned as a reflector. The orange line is the real resistance, the R, and the reactance is in this kind of a greeny color, and the phase is shown here, which is indicating resonance at about this point, which is entirely unimportant for this exercise. What is important is the very, very clear dip in the resistance. And as has been discussed at length through this video, this is entirely and solely a function of the tuning, the current tuning of the parasitic array. And this is what we use to anchor ourselves and tune the Yagi. So as we said, we'll use the 4NEC2 model as a guide to know exactly at what frequency we want to tune the driver for the desired bandwidth based on the experimentation and the various bandwidth runs that we did in the model. And then ultimately we'll fine-tune the array just looking at the bandwidth. So as I showed just moments ago, we did decide and agreed that, or at least I felt that this was perhaps the desired bandwidth for my array. That is to say, using something around a 30 kilohertz bandwidth. And I know that that occurred at 3822. If I tune in the model, the driver at 3822, that I'll achieve that kind of bandwidth. And that turns out to be approximately 20 kilohertz above the minimum R dip, as shown here. So here's my minimum R dip. Here's 3830, excuse me, 3822, where I want to tune the array. That's 20 kilohertz. So 20 kilohertz in this model with this Yagi, assuming I've built the Yagi comparable to the model, 20 kilohertz above the minimum R dip, the point of maximum coupling, is very close to where I want to tune the Yagi. So therefore, I look at my uh, analyzer sweep and I identify the frequency, and then at this exact frequency, 20 kilohertz above that, the dip is where I will tune the Yagi. Or in the case of my 160 meter array, that's where I'll tune the driver. Um, the method for tuning the driver is described in my paper for the Yagi as well as for my 160 meter array, but uh, that's immaterial. We will just one way or the other tune the driver at this frequency. Fine tuning, as I mentioned, will be based on looking at the SWR bandwidth. That is to say, if after we tune for minimum SWR at this point, we notice that, for example, the SWR bandwidth is very narrow, say it's only 16 kilohertz, then I know all I need to do is retune the Yagi slightly higher in frequency until I achieve the bandwidth I want. Once that's done, with absolute confidence, we know for certain that this Yagi is tuned to its absolute maximum without doing any field testing or any other iterations to confirm that. So, in summary, in my opinion, this method, using an analyzer to tune a two-element array, is easier and more reliable than depending solely on modeled parameters or field testing. Frankly, to expect a plug and play result from a model can be quite elusive, especially with the short loaded design. There are the tuning of a shortened Yagi like this is extremely sensitive, quite frankly. The traditional approach, which I have used, is to find the resonance point of the reflector on the tower with the driver isolated. In other words, you open the driver and sweep the reflector with the analyzer, and then you basically will tune the reflector to match the model, which in the model you'll do the same. You will build your model to suit, isolate the driver, and then sweep the reflector, and then you'll tune the reflector to match. This is the traditional approach. My experience has been, especially with a loaded design, that the tuning can be very sensitive to small changes. Even with very careful diameter and taper calculations and model design, even small inductor differences and parasitic capacitance, unknown capacitance at the element mounts can upset the real world when the driver is reinserted in the circuit. It's not that it's not possible, obviously. This is a tried and true method for tuning a two-element array, but my experience has been, especially when you introduce the tuning of a hairpin coil as a match at the driver, it becomes extremely iterative and almost always involves field strength testing to have confidence that um, that the array is tuned properly. However, measuring with an analyzer and understanding and using the model as a relative, not an absolute guide, is the key to this method and tuning success. And hopefully I've shown the process and the method, and you can see that when you're finished, there's a high level of confidence that the array or the Yagi has been tuned correctly. And experience and actual results using this method has proven unquestionably successful. The front to back on my array and my Yagi is exceptional. So I guess in summary, the last thing I just wanted to touch on is, why even build a short loaded Yagi that has such narrow bandwidth and such a complex requirement for tuning. The truth is, I have actually received some emails in personal correspondence, been asked, um, why have you even, undertaken building such a complex system? Those that have perhaps some have visited my web page and my Yagi web page, and I've got, looked at my relay boxes, 8 relays at each element with 18 band segments, and all of the associated complexity. Why why did you even do that? And I guess you know there's no question a full size Yagi, or say a OWA design or a Moxon design and so on and so forth. There's no question they will indeed show better SWR gain and even front to back bandwidth performance. I mean, that can't be argued. But excuse me, hopefully I've shown here that those bandwidth limitations can indeed be overcome with that complex band switching, and at least come close to maintaining, maximizing the gain in the front to back performance. One thing I will add is that if and there may be some designs out there, perhaps commercially available or homebrew, where you've got a short-loaded design that does not include any kind of parasitic and driver in-band element tuning. In my opinion, those will never be a top performer, because, as I said, there's simply no free lunch. And when you've got a loaded parasitic element, that's going to greatly diminish the bandwidth performance. Without switching, you're not going to have a winner, in my opinion. I would add that if you do give careful attention to minimizing your losses in the inductors, for example, the high Q loading coils, the ones I use, 6-inch diameter, 6-inch long copper tubing high Q coils, and if you're also careful about minimizing the series losses at the low impedance feed point, then you can at least come close. I'd say perhaps within 1 dB of a full size design. So obviously, it all comes down to a compromise, and I figure that really the decision is simply, is that added complexity and loss 1 dB or so of building that loaded design, is that worth the added cost to build and maintain a full-size antenna? I mean, if you're talking, especially on the low bands of a full-size 80-meter Yagi, that's a major, major undertaking. And is that, and with that would perhaps come less certainty about the mechanical longevity. And also, those monsters can really add a lot of strain on a tower and a rotator because of weight and wind load. Regarding that, the 80-meter Yagi here, the 40-meter Yagi here, is the same Yagi, the same mechanical design and construction, has been in service for 17 years here at V6WZ. So, everyone's going to have a different answer to that, and there's no question that for some the answer is absolutely full-size Yagi, and the simplicity of that is worth it. But that's hopefully that's it. Hopefully this video has provided some insight and some ideas, if nothing else, some ideas about methods for tuning and modeling a shortened parasitic design for especially, I think, the low bands. Anyway, thanks for watching. This is Steve, over and out.